the signal and you give Good evening. Konnichiwa, Здравствуйте, Wei, Guten Tag, Shalom, Aloha. Welcome to another event from the Data Science Group. We're here at the University of Colorado, Denver, in sunny Denver, Colorado. We'd like to welcome all of our friends at Big Data Week. Thank you for joining us. We have an incredible show today of Spark Sharp data analytics stack on a Hadoop cluster. I'm Michael Walker, and along with my colleagues, Michael Malik. Michael will be discussing and demonstrating the Spark Sharp analytical ecosystem. Chris Deptula will be crunching some numbers and showing us some wonderful data visualizations from Pentaho. And I'm Michael Walker. I will be doing a data science use case for us. Speed kills. Speed kills. What do I mean by that? Well, in technology, in data science, and the National Football League, speed kills. So while the title of this event is Spark Sharp Hadoop, the theme is speed kills today. Big data is a very overhyped term right now, as is data science. There's a lot of different definitions, and there's a lot of misimpression, unrealistic expectations about what big data is and about what data science is. There's many different definitions of what a data scientist does, and I say it's okay. It's a new field. We're just developing it, and that it can be anything that provides a solution. This is an interesting cycle of hype for emerging tech in 2012. It's by Gartner. And if you look here, big data is going up to the peak of inflated expectations. And a lot of people think it's in a big hype cycle right now. That may be true, but it may be anywhere along this line. What I find interesting is comparing it to predictive analytics, which is what a steady guide of what data scientists do. So basically you're saying predictive analytics, speech recognition, and text analytics over here, which is coming out of the disillusionment sector, in-memory analytics. This is all becoming very big. So it's interesting that there's a contrast. This is the hype cycle for big data in 2012. You can see here data scientists are over here, but again, we see here predictive analytics. What data scientists do a lot of is over here, along with web analytics and social media and supply chain analytics. So I think that there's a contradiction, and you need to take these hype cycles with a grain of salt, but I do think there's also an element of truth involved with them. We have a problem. And our problem is with the existing architecture of data warehouse business intelligence systems, which were designed to handle only internal data and structured data. And basically, it was designed to handle information data that's created and disseminated within the four walls of an organization. But today, you have unstructured data as well as structured data, and you have external data as well as internal data. So the new design really involves a new massive set of new data, and data virtualization has to be a part of that in order to handle this massive set of new data. This is an example of the next generation of data architecture, which is going to have to handle audio and video images, text, web logs, social graphs, sensor data, spatial data, and other things, and as well as structured data, as well as different types of databases, SQL databases, NoSQL databases, new SQL databases, and be able to handle this all within the organization. And that's a tough architectural design to put together. Any architectural design needs very good, fast data-based systems. So here is Gartner's Magic Quadrant for 2013. It just came out a couple months ago. And it shows Oracle, Teradata, IBM, SAP, Microsoft, and I would say HP Vertica probably belongs up into this quadrant. They all put together and build very good database systems. Now, I came across a statistic a few months ago that blew me away, and I think it may blow you away also. 90% of all data in the world was created in the last 2 years. Again, 90% of all data information in the world was created in the last 2 years. So we're going to have an enormous explosion of data. But as this chart shows, most of it's going to be unstructured data. That's the red here. The structured data is only set to grow this much. So we've got a ton of messy, noisy, unstructured data that we need to deal with. And as data scientists, we need to extract meaning from. This is also a good diagram of the structured versus unstructured data. You've got internal sources, emails, call center transcripts, external sources, social media. Internal, you have financial transactions, customer relationship management, all going into human analysis, data scientists, business analysts, text mining, and the results of it being able to be disseminated to people in the organization in a way that they can understand it simply and quickly. This is what we're building today. It's the new data analytical ecosystem. The blue here represents the traditional data warehouse design, which is a top-down architecture. The pink over here represents a bottom-up architecture, which is the new data analytical ecosystem that we're building. Now, our organizations have spent tens of millions of dollars in the last 10 years putting together a flawed data warehouse BI system. And so we have to live with it. So it's very challenging. You have to basically build ecosystems around it. And a big part of doing a data analytical ecosystem for organizations is Hadoop. And we'll talk about that in a minute. This is a wonderful visualization and a great example of visualizations that can tell a story in a very short period of time, or it would take me an hour to explain this. But in a nutshell, you have a whole bunch of different technology for big data analytics. You have infrastructure, you have analytics, you have applications, you have data sources. And a lot of time is spent doing technology selection, because you have to find the right technology for the right organization. Some technologies will be right for a certain type of organization. Other technologies will be the right fit for another organization. And it takes a lot of time and work to figure that out. The Internet of Things. The Internet of Things is basically putting sensors on all organic and inorganic things. So once we do that, the game really changes, and it's going to produce a massive tidal wave of data, because health data from my body, data from your car, from your washing machine, it's going to be able to talk to each other, talk to other computers, talk to us humans, and data scientists are really the people that are going to need to create meaning from all this data. You know, how many people have heard about the 3 V's of big data? Volume, variety, velocity. Well, there's a 4th one that I think is more important, and that's data veracity, data quality. I think that we need to have a standardized data quality rating system so that we Don't confuse the consumers of data science with results that may be flawed because the data quality is poor. Data scientists are a lot like carpenters. You got to pick the right tool for the right job. And of course, that means you have to pick the right database. NoSQL, SQL, NewSQL, row-based columns, key value stores, document stores. You know, you pick the right database for the right job. And it's very difficult. You have to spend a lot of time and brain damage figuring out what the best database to solve your particular challenge is. Hadoop. Well, there are a couple of advantages to Hadoop. One, it's cheap. It's open source. The second is it can handle a hell of a lot of data. You can store a ton of data cheaply on it. There are two big disadvantages to Hadoop. It's very complicated. It's not easy to learn how to use, and two, it's slow. And what did I say earlier? I told you, speed kills. To analyze large data sets, you need a lot of speed, and Hadoop has a problem. This chart gives a nice overview, Michael Malik will explain Hadoop and the Spark system more in detail. This is interesting. There are a lot of vendors that are focused on the NoSQL and Hadoop market. The top three are MarkLogic, Cloudera, and Tengen. This is growing enormously in the last 10 years, and there are a lot of smaller companies on this tail end over here that certainly have a chance to do very well and surpass many of these players. We're still very early in the game. This is a diagram of big data analytics infrastructure. There are a lot of things to know about big data. There's a lot of things to know in data science, but data scientists really need to have a big picture outlook and understand a little bit about all of these things and how they fit together. Thank you. I'm going to pass it over to Michael Miller.
So I named my talk a little bit of a provocative title here, Spark Ecosystem. Normally, we apply the word ecosystem to Hadoop just because there are so many pieces that fit into Hadoop. So by calling it Spark Ecosystem, I'm sort of hinting that maybe Spark can replace Hadoop, and that's sort of a war that's been waging on the message boards, and we can wage it at Old Chicago as well. This is my agenda, and I just want to give some hope to all the Hadoop experts here that I will be getting to the Spark stuff, but I am going to have to go through some Hadoop 101 here. Hadoop gives us two things. It gives us HDFS, the Hadoop Distributed File System, which is distributed storage, and it gives us MapReduce, which is distributed computation. Here's HDFS. This is showing the storage of a single file. When you store a file onto HDFS, it breaks it up into 128 megabyte blocks, and those are shown by B1, B2, and B3. A Hadoop cluster, you know, it might be 10 machines, it might be 100, it might be 1,000 machines, but it's arranged in a master-slave relationship with a name node having the list of all the file names on your HDFS and a bunch of slaves called the data nodes. And this is showing the storage of a single file here. It's broken up into 3 blocks, B1, B2, B3. And you can see that B1 is stored onto data node 1, 3, and 4. B2 is stored onto data nodes 1, 2, and 4. So there's replication going on here. This is showing a replication of 3, which is pretty typical for Hadoop. So if you have 300 terabytes of storage combined across all the nodes in your cluster, it means you can only really store 100 terabytes of actual data. And of course, replication means that if one data node goes down, Hadoop will automatically recover and replicate those blocks onto the surviving nodes. So that was distributed storage. This is the distributed computation of Hadoop called MapReduce. And if we look at the upper right corner there, that shows sort of the high-level data flow. MapReduce allows computation over a very large data file. So if we have, say, a 100 gigabyte data file, In this diagram, you might break it up into 20 gigabyte chunks. Each 20 gigabyte chunks goes into a mapper. The mapper does some sort of transformation, possibly also some filtering. You can see that second mapper from the bottom actually chose to not pass any further data on. The outputs of the mappers go into a shuffle sort. They get sort of coalesced together by key, and then those coalesced versions go into the reducers, and the reducers spit out a final value. They do some sort of computation that reduces the data, maybe just adds up all the numbers and comes up with some counts. This diagram down here shows the physical layout. If you look at the bottom half of this diagram, it shows what we saw for HDFS, where you have a master called the name node and the slave called the data nodes. The MapReduce also has a master-slave relationship with the job tracker being the master, the task tracker being the slaves, and individual tasks are just pieces of maps or pieces of reduces. So that's Hadoop in a nutshell. And what's wrong with this? Well, Google wrote about this 10 years ago, and Hadoop came out 8 years ago. But the trend in 2013 is to bash MapReduce. And what's wrong with MapReduce? Well, there's actually nothing wrong with the concept. But there's a couple of things wrong with the implementation in Hadoop. The first problem is the communication between the job tracker and the task tracker. You submit a job to the job tracker, and 30 seconds later, the task tracker will tell the job tracker, "Hey, I don't have anything to do. You got something for me to do?" So it's sort of a polling operation rather than a push. It was just easier for Hadoop to implement it that way way back then. The other shortcoming of MapReduce is, we have all these machines in our cluster, and HDFS make great use of the hard drives to store data, but there's not a lot of great use of the RAM. Well, I mean, if you're watching the control monitor on your Hadoop cluster, you'll see the RAM usage spike up during some of these MapReduce computations. But nothing ever gets cached in there, and that sort of becomes really important if you're trying to apply any type of iterative algorithm. I mean, you can think of a MapReduce operation as sort of like a single for loop. But what if you have a nested for loop? Any sort of iterative machine learning algorithm where you need to preserve the results from one MapReduce operation to the next, and Hadoop out of the box doesn't give you that. A lot of the proposed replacements for MapReduce do. There's kind of a third problem with MapReduce that's long been solved for many, many years, almost as old as Hadoop. And that is, if you were to write base MapReduce code in Java, it requires 100, 200 lines, or hundreds of lines in some cases. And so there are these tools that are long-standing that simplify the task of writing MapReduce code. Pig came out of Yahoo. Hive came out of Facebook. Pig and Hive are kind of similar in terms of their use case in that they just look at raw HDFS files, and you write queries in a very high-level language to implement MapReduce against those raw HDFS files. Hive is quite a bit more popular because it uses HiveQL, which is a subset of SQL. And by subset, there's quite a bit of restrictions. Well, first of all, there are no subqueries, but really the more severe restrictions are there's no in-place update. I mean, these are just flat files on HDFS on your file system. So you can't update in place, you can't delete in place. If you want to do an update or delete, you basically have to copy the whole table over again. And that's where HBase comes in. HBase maintains Delta files, and every so often it regenerates itself. We're going to be focusing on sort of the Hive applications, because everybody's so familiar with SQL and it supports HiveQL. So these are some of the proposed replacements to Hive. Hive can be a frustrating experience. I mean, like all SQL tools, you sit down at the command line and you enter your query, but with Hive, your answer can come back in half a minute or 10 minutes. And that's just a frustrating experience, because if you're trying to practice data science, you're going to be doing some repetitive queries, some exploratory analysis. And so everybody loves to bash Hive and say, oh, we have a replacement for Hive that's 100 times faster. And, well, I guess they do. So these are some of the major Hadoop distributions. I guess the older ones. I mean, there are newer ones coming online all the time. Intel has announced their own Hadoop distribution. Microsoft has announced their own Hadoop distribution, both of them in the last 2 months. But MapR is, this is the Apache Drill logo, is promoting Apache Drill. And Cloudera is promoting Impala, Hortonworks is promoting Stinger, and Greenplum is promoting Hawk. And I use the word promoting because all of these Hadoop vendors, of course, Hadoop is open source, so these vendors are selling support. And actually MapR does have some proprietary code. But in the case of these Hive replacements, they have committed to keeping them open source. There are some other Hive replacements that are not particularly tied to a Hadoop distribution. That's Druid and Spark. And Druid and Spark have another thing in common. Besides being just not being associated with a particular Hadoop distribution, they also are good for streaming, which is the next wave that we're going to be talking about. It's going to be cool to do Hive 100 times faster, but it's going to be ultra cool to do the real-time streaming. And both Druid and Spark do that by consuming data in real time and leveraging the RAM across the cluster. A big difference between Druid and Spark. Druid actually kind of worries me a little bit in that there's like one guy behind it. Basically, a guy working in a company called MetaMarkets, and there was nothing out there that did what he wanted. No database, so he just sat down and wrote it. And then after he got it working, he begged his management to open source it. And so I don't really know how committed MetaMarkets is to supporting Druid over the long term. Spark, in contrast, has a lot of money behind it from the University of Berkeley. So actually, it's not a commercial venture; it's a university venture, but it's actually a 6-year project. And so this is what I was talking about. So if you're doing Hadoop, you're cool. Your first generation. If you're doing your 100 times faster Hive, okay, you're super cool. But if you're doing streaming data processing, streaming big data, that's where the ultra cool stuff is. And right now, your choices are either Druid or Spark, and there's actually a third option called Storm, but that has some performance problems, although it's a very popular choice. This is the commitment I was talking about at Berkeley. Berkeley actually set up a Silicon Valley style skunkworks here with 40 students, mix of grad and undergrad, 8 faculty, and 3 staff software engineers. It's a 6-year project, and they're only 2 years into it. This is the stack, the Berkeley Data Analytics stack. The first interesting thing is this layer called Mesos. This is actually an operating system for your cluster. So putting Spark aside for a moment, let's just say you have your production Hadoop cluster. It has 50 nodes. Okay, well, if we're going to practice good enterprise software development and governance, we're going to need a development cluster. We're going to need a test cluster. We might even need an acceptance cluster. Well, all of a sudden, our 50 nodes becomes 200 nodes and 4 times the budget. Mesos allows you to dynamically allocate physical nodes to a particular Hadoop cluster. So you can have your physical cluster of 50 nodes and dynamically partition that into multiple Hadoop clusters. Or you could have 2 Hadoop clusters and 1 Spark cluster. So Mesos is kind of this shim that allows Spark to sit on the same physical machines. Spark makes use of HDFS. It does not replace HDFS, but Spark does, the main thing Spark does is it replaces MapReduce. As an aside, it may actually be theoretically possible to even get rid of HDFS, I don't think anybody's tried it, but on the message boards they're talking about, well, Cassandra exposes an HDFS API, so you may be able to run just Spark and Cassandra. Now, you can write, and it's actually very useful to write a Spark app directly onto Spark. That makes use of the Spark's MapReduce replacement, and that is useful and performant. But even more useful are these other subsystems. And all three of these subsystems that I've listed here are coming out of Berkeley, so they're strongly supported. Bagel is for graph processing, like Google Cradle. And I'm not going to go into Bagel too much, but I'm going to go into Shark a little bit, and that's really what Michael and Chris are going to go into after I talk. And I'm going to go into quite a bit of depth of Spark streaming. So Shark is the high replacement, and Spark streaming is the interesting streaming piece. So this is Spark 101 here. The base of all Spark is the RDD, the Resilient Distributed Data Set. So instead of distributing your data across a bunch of spinning hard drives like HDFS does, RDDs and Spark distribute your data across the RAM contained in each of these nodes. It's resilient because data is replicated, similar to HDFS, distributed, as I said. Now, the acronym RDD doesn't include all the aspects. Another aspect of RDD is that they are immutable. Spark is written in Scala, which is compiles to the JVM, which is really about the only thing it has in common with Java. It has a philosophy of functional programming, although you can program any number of styles in it. But this philosophy of functional programming, where you have immutable data and lazy evaluation, it's part and parcel of Spark itself. You can address the Spark API from either Scala, Java, or Python, but I recommend Scala just because it's the native language. So this is an illustration of the laziness. Okay, so the first line does something, it reads in a text file, but the next three lines do nothing. Nothing happens until the last line, which is an action line. And this ties into the immutability. So the data is just sitting out there in your RDD, in your cluster, and nothing happens through these three transformations. The transformations are just sort of queued up, and then when you finally get to a command that is not a transformation but an action, that's when everything, the whole processing queue gets flushed and processed and output. And I'm not going to go through these, but I just wanted to illustrate in the Spark documentation, there's a great distinction between what's a transformation, in other words, gets queued up, is lazy, and what's an action, what gets executed immediately. And this is one of my little cheats here for people new to Scala. The brackets are templates, like angle brackets in C++ and Java. So Shark is a layer on top of Spark. So I just went over the basic Spark RDD MapReduce replacement. Shark takes that MapReduce replacement and that leverages it to come up with something that speeds up Hive. So Hive, like I mentioned earlier, it just looks at raw flat files sitting on your HDFS cluster. Shark allows you to look at a combination of HDFS files and RDDs that are sitting in the RAM of those nodes. And this is just the exact particular syntax where you can do it. These could just be Hive commands, except for a couple of things here, where we're doing a create table, and we specify this extra little table property, shark.cache equals true, and that this command is basically taking a table out of HDFS and copying it into permanent cache on as an RDD. And then this is just some syntactic sugar that they give you. You don't even have to specify this table property. You just add a suffix to your table name, underscore cached, and when it creates this table, it copies in your data from this other table called wiki that's sitting on HDFS and keeps it in your RDD. So this is very useful if you're going to be querying this table over and over again when you're doing your exploratory or data analytics. Now here's the dirty little secret. Shark is only 7 kilobytes of code. It actually, I keep saying it's a Hive replacement. It actually just sort of replaces parasitically some of the key parts of Hive. So actually, when you hit Shark with a Hive query, you're actually going through the regular Hive query processor, but the guts of it have been replaced here with these darker rectangles. So a legitimate question that astute people might be asking is, well, is it really big data if you're limited to the RAM, the combined RAM of all the machines on your cluster? I mean, is that, yeah, because when we talk about big data, we often talk about petabytes. And then, there's some truth to that. But a lot of data science happens down here. So, I mean, you get your raw logs, whatever, your raw data. A lot of it is just not of interest to you. You do your boiling down of data, first to the terabyte level, then to the gigabyte. I mean, eventually you're going to come up with your single number or your single graph that's a few kilobytes. But a lot of the iterative, repetitive querying is going to happen in this range. And to get a terabyte of RAM on a cluster is no problem. I mean, to get a terabyte of RAM on a single machine, it's going to be no problem for a cluster of 10 machines or more. And just to reemphasize this, I stole this slide from the author of Shark on their presentation. They captured this tweet that the median Hadoop job input size is 15 gigabytes, which makes you wonder if you even need a cluster at all. I mean, that's what you get down at Micro Center. So that was Shark. I'm going to go on to Spark Streaming, which is the really cool part of Spark. So this is a typical use case for Spark Streaming. So you have a video game over here, times 1 million clients, and you want to dashboard that. Okay, you want to monitor the operations, make sure you're not getting too many errors, and also, a lot of the revenue from video games these days comes from in-game purchases. You have to purchase all these shields and swords. So you might want to monitor dollars per player per hour. What if your merchant account goes down? I mean, you don't want that to be pegged to 0. But at the same time, you don't want to give up your traditional big data collection. So we're also going to pipe the data off to HDFS so that we can do our offline analysis with our conventional BI tools like Tableau. So how does Spark Streaming accomplish this? So it doesn't do it by a pure stream. It does it by small batches. So small batches of, say, 2 seconds each. Some people do half a second, some people do 10, 30 seconds. But it's a sequence of RDDs. So all the events that came during that 2 seconds get bundled into an RDD, and because it's now in an RDD, you can apply the baseline Spark API. And this sequence of RDDs is called the DStream. So this is quite a lot to wrap your head around. This is actually 2 levels of indirection. Right? So the first level of indirection, if I tell you I have a DStream, well, you have to unpackage that twice. First you have to unpackage it to get your RDDs, and then within your RDDs, then you have to get your individual events. Now this is a directed acyclic graph. So this is the example. You could call this whole thing a directed acyclic graph, but within this whole acyclic graph, there's something specifically called the DAG that I've highlighted with this blue field. And this thing called the DAG is a very special thing to Spark streaming that you'll see. Each of these arrows is a DStream. So remember what a DStream is. Every 2 seconds, it's going to be spitting out an RDD. And within that RDD will be all the events from within that 2 seconds. And this is all high-level stuff. Oh, in this example, I'm showing the data source is coming from Kafka. Kafka is a message queue that's popular to use with big data. It's very deep, very resilient. And Spark streaming has a connector directly to Kafka. Kafka also happens to be written in Scala, so it's a good match. If you're doing Spark streaming, you're almost certainly doing Kafka, because really the only other consumers are from a fixed text file or from Twitter for demos, which I'll actually show you at the end. All right, so now we're going to get into some actual code here. No more fun stuff. The interesting thing here is the mix of types of code here. This all looks nice and linear and imperative, but it's not. And this was actually very confusing to me when I first started with Spark streaming, because I was not only coming up to speed on Scala, I was also coming up to speed on Spark and Spark streaming all at the same time. And these lines here under the DAG section actually don't get executed. These are purely declarative. They're kind of akin to Visual Cafe back in the 90s with Java Swing, or even C# from the mid-2000s with .NET, where you sort of declare your GUI and connect everything up together. This is just connecting up the DAG together. It's saying this input is going to this output, and that's it. It's not actually applying any of these filters or any of these for eaches at the time of invocation. It's just hooking everything up. And then finally, when you get down to the start, that's when it turns on the faucet, and that's when everything flows from the DAG that you just declared. I'll go through some other little Scala tidbits over here. This underscore is used a lot in Scala for many different things. In this particular case, this is shorthand for X maps to X dot. It's so this is a lambda expression in an anonymous function. And another Scala tidbit here, these double parentheses here. This is actually instantiating a new tuple2. So I think Java has something called a pair, or C++ also has a pair. This is the same thing. It's just Scala is very terse, and you can omit things like new. So this is instantiating a new parent. Now, if that wasn't complicated enough, this previous example, this is good for, okay, so in this 2 seconds, users are experiencing errors. Okay, the next 2 seconds, users are experiencing errors. But there's no memory recollection of what has happened in the past. And in this example, what we're doing here is we're trying to count the number of users currently logged in who have ever experienced an error since they logged in during their current session. And to do that, we need to maintain state. And this update state by key is one of the more advanced and more useful features of Spark streaming. I have to do a little bit of a digression here. Update state by key, I have to talk about what key is. So here I'm mapping my events into a tuple2, where the first part of the tuple is the user ID, and the second part of the tuple is just this dummy value 1. So this user ID is serving as my key. And so update state by key is going to group all the events for a particular user together. And then this callback function, update function, is going to get called once for every user, and it's going to get passed in a sequence, which is just a smaller collection of those events. And it's going to get passed in this magic state that Spark Streaming magically maintains for you somewhere. When you get that state, you can update it. Here I'm incrementing the number of errors. And then when you exit this function, you have to return one of two things. You either just return the state variable itself right back out again, and option is just a Scala wrapper class for handling nulls, or you return none, which is Scala for null. If you return none, that says, I'm done with this user. The user has logged out, and Spark Streaming, you have my permission to delete that state. Otherwise, if you return option state, it tells Spark Streaming to maintain that state. And this allows you, it's very powerful because it allows you to maintain total control over the retirement of state. You can base it off a log off event, you can base it off a timeout, or a combination thereof. See anything else before I move on? All right, yeah, and if you were to intuitively think about this, you might think that, you know, from this DAG point of view, that we're only going to be getting you know, this function is only going to get called for events that happen to come during the 2-second period that happen to appear in our current RDD. But thankfully, the designers of Spark Streaming didn't follow common sense, and they made it very convenient and powerful to the programmer. This gets called for every state that is still being maintained by Spark Streaming. So that's where I was saying you can do a timeout, and it allows you total control over the retirement of the state. So that was Spark Streaming. There's some other Spark subsystems out there. I mentioned Bagel, which is coming out of Berkeley. There's some sort of independent research alternatives out there that I don't know if they're even released yet, but Sparkler does matrix decomposition, and then a company called Impetus is doing some machine learning based on Spark. I went to a talk of theirs at Strata a couple months ago, and the guy actually referred to Spark as a third-generation machine learning tool. What he meant by that was, you know, if a single computer is first generation and Hadoop/Mahout is second generation, then Spark is third generation. And the specific example he gave was that, you know, Mahout can do linear SVM, support vector machines and machine learning, but Spark is powerful enough to do nonlinear SVMs. And just to give a teaser for my next talk a few months from now, and just to illustrate how hot the topic of streams is, there's actually a book out now, it came out a year or two ago, on machine learning data streams, where you're doing some incremental machine learning, so you can track changes in data as it goes on, maybe tracking outliers for potentially fraudulent activity. And so what this guy has done, he's taken traditional machine learning algorithms and made them incremental so that you forget really old stuff and then you add on new data without having to recompute everything in the middle. And I'm going to give a little bit of a demo on Spark Streaming here. The computer I was intending to give it on died about 3 hours ago, so I've incorporated it into a PowerPoint. All right, Chris. Oh, there's an extra point slide there. I guess I put that in. There we go. So this is going to introduce yet another Spark Streaming topic, and that is reduce by key in window. So I've been talking about 2 seconds, 2 seconds, 2 seconds. Well, you might want to update frequently, but have a longer look-back period. And that's what reduce by key in window does. This is utilizing Twitter as the data source instead of Kafka. This is used for a lot of demos. And in this example, we're going to have a couple of data streams. We're declaring a DAG here that splits the data stream into two, one that is has a look-back period of 60 seconds, and one that has a look-back period of 10 seconds. And the output of this is the most popular hashtags. It's not going to be the most popular hashtags over all of Twitter. I think it might actually just be the subset of my personal account. And let's see how I play this. Get the play button up here. And so this is me 3 hours ago at my desk. Yeah, so only five tweets, not all of Twitter. And you can see both streams are outputting here. And that's it. I'm going to turn it back over to
Speed kills. Speed kills. I told you I'd come back to that, didn't I? So I was thinking, do you all like NFL football? I love NFL football. And I was thinking the other day that the best NFL offenses have been using a up-tempo, no-huddle strategy. And I thought to myself, wow, is that, really true? So I created a hypothesis. And that hypothesis is that NFL teams using an up-tempo, no-huddle strategy have the best winning records. So how can a, data scientist go about testing this hypothesis? Now, when we say up-tempo, it could be variable tempo, but it does mean at certain points in time, it goes faster in addition to the no-huddle strategy. So what data scientists do is look to formulas, and this is just one among many. I could spend 3 two-hour presentations just talking about the different things in this diagram. But what you need to take out of it today is you have information, you have scheme, you have insight, and you have a product. And you need to do it according to scientific methods. It's data science. And if we don't use scientific methods, it's really not science. And, in a nutshell, it means you have a hypothesis, you test that hypothesis, you get the results, you try and replicate the results or reproduce the results, and you do cross-validation. So what we did is we collected data on all NFL offenses. We collected data on NFL offenses using an up-tempo, no-huddle strategy, and collect data on NFL team records. But you may be thinking to yourself, well, how can you tell if an offense is using an up-tempo, no-huddle strategy? Well, there's a little bit of a subjective classification here, but the way I did it so that you could use hard data, as I said, teams that run more plays during the game are using an up-tempo, no-huddle strategy. So what do? We compare the data on NFL offenses with all NFL offenses with data on the offenses using an up-tempo or variable tempo, no-huddle strategy. And we have a whole bunch of different tools that we can use here. Just for the sake of simplicity, I decided to use a simple regression analysis. There are three types of data analysis: descriptive, predictive, and prescriptive. Descriptive is what the current data warehouse business intelligence systems use. It's about studying the past, what happened in the past. And that's important, and it has a lot of value. Predictive is forecasting what is most likely to happen in the future. And the holy grail of data science is prescriptive, which is optimization and simulation. How do we get to where we want to go? How do we win football games? How do we make sure we get to the playoffs, get a ticket to the dance, get into the Super Bowl, and have a good shot to win the Super Bowl? How do we do that? Well, we got to look at what's happened in the past so that we can formulate some sort of plan, but we also need data science techniques to make some forecasts. So predictive analytics is very, very popular right now in business, in government agencies at all levels are starting to use it. Some for good purposes, some for not so good purposes. And we're really in the pre-industrial age in data science in terms of developing different methods to make predictions. I can tell you the two that data scientists use most, and that's Bayesian probability and Monte Carlo simulations. And again, it's about probabilities. I can't really predict what you are going to wear tomorrow. But if I look at past data and I create some models, I may be able to create odds saying that somebody is likely to wear a brown sweater tomorrow, giving a 60% chance. It's just so we understand that this is not an exact science where we can actually do exact predictions. So it's interesting that KD Nuggets did a poll of the most popular predictive modeling techniques, and the three top ones were decision trees, regression, and clustering. But again, data scientists are a lot like carpenters. You use the right tool for the right job. This is an interesting chart from Gartner, really describing descriptive analytics, what happened, diagnostic, why did it happen, predictive, what will happen, and prescriptive, how can we make it happen. Data science really concentrates on this area. Traditional business intelligence has concentrated on this area in here. This is just another way to put it. Again, predictive analytics has to do with simulation, forecasting, modeling, what will happen next, what if these trends continue, what could happen, what actions are needed, and then prescriptive does a lot of optimization with scholastic optimization. How can we achieve the best outcome, including the effects on variability? How can we achieve the best outcome? How can we win football games? That's tough to do in the NFL. What did I say earlier? Speed kills. That's how you win football games and get very fast players. So I said we decided to use a regression analysis, very simple regression analysis. And a regression analysis is really just exploring the relationship between two variables. And in this case, we wanted to explore the variable between the number of plays each team ran in a time period and average per game, and how many games they won. So we took some data sources. InfoChips has a wonderful data source, NFL games, each play-by-play from 2002 to 2009. Now it's interesting, I talked about data quality earlier. We found some data quality problems with this data, and we did a very crude model of rating the data quality on a scale from 1 to 10, 10 being the best, very high quality, 1 being very, very bad. We came up with about a 7. This is a human guess. So this data has some problems, and I think the data scientist needs to fully disclose that to the client. There's a lot of noise in this data. But that said, we're doing really some simple regression analysis using some basic hard data, and most likely the problems in the data quality is not going to affect the results of the science that we're doing. But in other areas, other hypotheses, it definitely would affect it more, and you have to be very careful about it. Oh, also, I supplemented the data with data sources from Database Football and ProFootballReference.com. I will make this available on the site, and you can download this data, you can slice it, you can dice it. It's fascinating, the different stats that you can find. For example, one statistic Chris was telling me that he found the other day was that the last 2 minutes of the first half, in other words, the last 30 minutes of football, has the most points scored. Why would that be? I mean, there's a lot of different hypotheses, but they're in a 2-minute offense, and a lot of teams want to score before they go into half to get momentum. I would have thought that the end of the game, because many of the NFL games are very close, that the 60-minute, 58, 59, 60 would score the most points. But that doesn't seem to be the case. In fact, it's a huge disparity. So you're going to find interesting statistics like that. So I looked at the data, and first of all, I want full disclosure. You need to be careful about your own biases. I have no connection to either the New England Patriots or the Oregon Ducks. I was born and raised in New York City, big New York Jets, New York Giants fan. When I moved to Colorado, I became a big Bronco fan. I love the Broncos. I have nothing to do with the New England Patriots, nothing at all. But I found the New England Patriots most consistently in that time period used an up-tempo or variable tempo no-huddle offense. Also, I found the Indianapolis Colts, led by Peyton Manning, used a no-huddle, but not up-tempo most of the time. Sometimes they would do an up-tempo, but most of the time Peyton Manning they'd have no huddle, right? And he'd bring all the players up and they'd line up, and he'd start barking orders, blue 36, blue 36, and he'd be moving people around and waving his arms, but it took a long time for them to snap the ball, whereas the New England Patriots more frequently just went to the line of scrimmage, forgot the huddle, and snapped the ball very quickly. Not all the time. Sometimes they would delay, so there was some variability in the timing there, but a lot more times. In college football, there was a lot of teams are using the up-tempo, no-huddle offense, but one team that has done it better and more consistently than anybody else is the Oregon Ducks. So, data modeling, you got to create a model for your data, but if somebody else has already created a model, and there are hundreds of thousands of different data models out there that does the job, you're better off, not reinventing the wheel. You can borrow somebody else's data model if you need to. You can make a few tweaks here and there, but you need to know how to create models, because there are going to be those cases where nobody has created the model and you need to build it yourself from scratch. But if somebody's done a fantastic job, borrow their model, use their model. And Aaron Schatz of Football Outsiders created a wonderful model that I could not improve on. It's called the Defense Adjusted Value Over Average, DVOA. And put simply, all it really means is that he's averaging out a lot of different variables, including the quality of the defense that that the team is facing. So let's look at some data real quick. Here we have the 2001 offensive efficiency ratings, and we find that New England is 16th, but they had a pretty good record, 11-5. I think this was the year that their quarterback, Drew Bledsoe, got hurt, and Tom Brady, an unknown 6th-round draft choice, took over. And he actually led them to the Super Bowl that year. They won the Super Bowl. They beat the greatest show on turf, the St. Louis Rams. They had a 14-2 record. I think during the Super Bowl, the odds makers for St. Louis, I think, was at least 10 points favored in the betting market. So everybody thought St. Louis was going to absolutely kill New England. Of course, that didn't happen. The Patriots won. The next year, 2002, New England improved greatly. Now they're up to number 7. The next year, 2003, they're number 4. Next year, 2004, that was the year I think Indianapolis went to the Super Bowl. They did very well. Number 3. 2005, number 7. 2006, number 5. 2007, number 1. Hey, this was the year, remember, they went 16-0, and if they would have won the Super Bowl, they would have been only the 2nd team next to the Miami Dolphins to have a perfect season. But the New York Giants, who aren't even on here, beat them. So that's interesting evidence. And they slipped in 2008. They went down to 11. I think this is the year that Tom Brady got hurt and Matt Castle came in. 2009, they're back to number 1. Tom Brady's back. We jumped to 2011, number 4. Still pretty good. And this is the year Tim Tebow was quarterbacking for Denver. And I love Tim Tebow. He was so entertaining. Those were fantastic games to watch, but we were only ranked 24th. So had a few offensive issues. 2012, this is last year. Number 1, New England. Number 2, Denver Broncos. Peyton Manning led Denver Broncos. So this is interesting just to compare the average DVOA with points scored. And there's a pretty close correlation. Not perfect, but this suggests that he's got a good model. Here, this is kind of interesting. The best all-time offensive DVOAs from 92 to 2011. New England gets it 1, 2, 3 times, and Indianapolis gets it once. So New England has a better offense than Indianapolis according to this model. Now, best pass offense, New England has it 1, 2, 3 times, but Indianapolis has it twice. That's interesting. Now, if you want to compare Peyton Manning to Tom Brady, Peyton Manning has the best DVOA of any quarterback in the league in 2004. I think that's the year they went to the Super Bowl. But he only makes this list twice, here and in 06. Tom Brady makes it 1, 2, 3, 4 times. Tom Brady's been the more consistent quarterback. Now, there's a lot of reasons for this. I mean, New England could have a better offensive line. You know, Tom Brady may not have better skills or be a better quarterback. There are a lot of other variables, and you need to keep this in mind. Now, here we get to the real meat, the number of plays per game. So we're really going to test out to see if I can prove my hypothesis. So the data, they really only start collecting data on number of plays run by a team in 2003. But in 2003, New England's number 1 at about 66 plays per game. 2004, they slide down to 7, but still pretty good. You know, out of 32 teams, you know, top 10 is good, top 5 is outstanding. But it slips to 64 plays per game. 2005, bad year, slipped to 15th, so 63. 2006, back up to number 4, 66. 2007, number 3, 65. Notice we don't see Indianapolis a whole lot on this list, do we? That's interesting. 2008, number 1. Again, I think this is the year that they went 16-0 and they had that great offense. 68 plays per game. 2009, number 2 at 67. 2011, second at 67. That's very interesting. So kind of hard to wrap your head around this, looking at all these numbers. What if we put it into a graph format? Do you think that it might help us to understand this a little bit better? Oh, I forgot 2012. New England's number 1 at 74. Denver with Peyton Manning at 69. But interesting, Indianapolis with a rookie, what's their quarterback name? Luck. Luck had them at 70. So when Indianapolis made the playoffs, they were a very good team. Here we go. So team record. So what is the relationship between number of plays a team runs and their record? That's really what I'm looking at. And does the data really support it? Well, Indianapolis has more team wins than New England. But that's still, that seems to be evidence against my hypothesis, except for it's only one game. And also, if you remember, I told you, Indianapolis runs a no huddle and a variable tempo. So it's not really comparing New England that runs a up-tempo, no huddle offense to a team that does the traditional huddle up and use most of the play clock. So there's some doubt in there. There's a little bit of noise in there, but definitely some disconfirming evidence, no doubt about that. Total points. Indianapolis scores a little bit more, not that much. So, maybe this whole up-tempo thing may not be what it's cracked up to be. This is some evidence against it. Then average points per game, but there's not that much of a difference. And remember, Indianapolis runs a variable tempo, no huddle, so it's close. So, total plays. This is interesting. New England, by far, runs more plays than anybody else. And where's Indianapolis on this list? It's not. They're nowhere to be found. They don't run as many plays. Oh, I'm sorry. So they're number 4. But a long ways away from New England. Thank you. I didn't see that. Average plays per game, well, again, there's a great disparity. New England is number 1 by far. Indianapolis is, 7th? So the data results. From 2001 to 2009, the Patriots had 107 wins and 37 losses. Second best record to Peyton Manning and the Colts, but by only 1 game. They appeared in 5 Super Bowls, winning 3. And if you extend the data set out to 2012, the New England Patriots have the best record in the NFL. Of course, Peyton Manning gets injured, so that complicates things a little bit. So I guess I failed. I can't prove my hypothesis. I show a strong correlation. There's a strong signal, but I can't prove causation. There are too many variables. But it's okay to fail. And who was it? It's the Rolling Stones, Mick Jagger. You can't always get what you want, but if you try sometimes, you just might find you get what you need. I got what I need. 5 Super Bowls, winning 3 Super Bowls. I mean, if you don't get a ticket to the dance, you can't dance with the pretty girl, right? So it's signaling something. It's signaling something. So again, Indianapolis runs a no-huddle offense with a variable tempo. New England runs an up-tempo, no-huddle offense. And in terms of number of points, scored only second to the Colts. But Indianapolis appears in 2 Super Bowls, wins 1. New England is in 5, wins 3. What does that tell us? What does that tell us? It tells us Peyton Manning, scratches his head and says, Tom Brady, son of a bitch. What is he doing? What's really the only difference? We both run no huddle. We run kind of a variable tempo. He runs an up tempo. Light goes on in Manning's head. Up tempo. We need to up our tempo. We need to run faster, so we run more plays. We run more plays, we score more points. We should win more games, but it'll at least give us a better chance to get to the Super Bowl. Last year, Peyton Manning comes back. What did he do? His first year in the Broncos. He runs a no-huddle, up-tempo offense.
He brings them up, he gets them live. What does he say? He says, hurry, hurry! Remember? You could hear him. You could hear him in Aurora. He said, hurry, hurry. Uptempo. Manning figured it out. That's how New England's been doing it. And so I predict other teams are going to follow. Now, it doesn't mean that it's automatically going to give you a winning record or get you to the playoffs or win a Super Bowl. It's about probability. And you got to have a really good quarterback. You know, and also you could have a very bad defense. So you could be scoring all these points and have an incredible offense, but your defense sucks and you know you're going to go nowhere. So there are too many other variables. But ceteris paribus, all things being equal, this is a good strategy. Huh? And look at the stats. New England from 2001 to 2012. You see this is plays per game, and this is their rank. So here 17 teams ran more plays than New England, but they had their offensive rating was 6, meaning that they scored more points than only 5 teams scored more points than them. They were Super Bowl champs. But then you see this start to increase. The next year they run 64 plays, that's 8. Next year 66. They're only 12, but they're running a lot of plays per game. They got a 14-2 record. They win the Super Bowl. Next year 14-2 record again. They're running 64 plays on average. They're 7th, 4th total offense, Super Bowl champions. They keep, it's very, very high. And even if you looked at their DVOA, they always seem to be in the top 10, except for a few years. So it's signaling something. There are only a few outliers. Here in 2010, they're 21st. In 05, 15th. In 01, 18th. But all these other years, they're top 5, top 10. It's signaling something. Now, I love the Denver Broncos, and I love Tim Tebow. Absolutely love Tim Tebow. Love the style of play. Here's the problem. Look, 2011, we were 8-8. Tim Tebow brought us back from games we should have lost in an incredible fashion. It was almost like divine intervention. And should data scientists believe in divine intervention? I don't know. We need to talk about that at Old Chicago. So anyway, they're running about 63 plays per game, which is 16. That's middle of the pack, but the ranking offensively is 25th, which is at the bottom of the league. John Elway looks at this and says, no matter how exciting it was, especially the playoff win against Pittsburgh, this is not sustainable. This is not sustainable. So Peyton Manning comes in and last year runs 69 plays per game. That's 4th in the league. That's really good. That's outstanding. 2nd overall, meaning only one other team scored more points. Which team? New England Patriots. So then I crossed some other data. I said, well, are there any other teams in the NFL that ran this up-tempo, no huddle? And the only team I could find was the Buffalo Bills. And I don't know if you guys remember, but they went to 4 Super Bowl in the early 90s. And they were a run and gun team. They didn't huddle. And I think they did a lot of variable tempo and a lot of up-tempo. And the only way to really measure it again is plays per game. So in 1990, their first Super Bowl, they only run 58 games, but their first overall in offense, they lose the Super Bowl. Next year, they're 13-3, which is an excellent record, but they're running 66 plays per game. And that doesn't look like a lot. It's 8 games. But over the course of the season, 8 games, that's going to give you a game and a half of extra plays, won't it? That adds up. So it does mean a lot. It means you're going to get more yards, you're going to score more points, you're going to have a better chance to win. Next year, they don't have as good a record, but they run 67 plays. They're 3rd. They lose the Super Bowl again, 12-4, 93, 67, which is very high at that, especially at that time. They lose another Super Bowl. So we have some evidence here that another team tried this strategy and was successful with it. Even though they didn't win the Super Bowl, a couple of these years, they were like a field goal away. I mean, a kicker hits a 40-yard field goal and they win the Super Bowl. So they didn't, and then I think 1 or 2 they did get blown out by Dallas. Then I looked in college, and all the great teams now are using Uptempo, no huddle. And because it gives you a huge advantage. The college coaches saw it, especially teams like the Oregon Ducks, who play in the Pac-12, where you have UCLA, Stanford, USC, Washington. These are powerhouses. These schools can have the best football talent in the world. Oregon Ducks, you're not going to get the best. You'll get good players, but you're not going to get the best. So you've got to find an edge somewhere else. Where do you get that edge? Well, you change the strategy. You change the rules of the game. So Chip Kelly comes in 2009. His first year, he institutes the Uptempo, no huddle, runs 68 plays a game, which is only 54, so there are 53 teams that are running more plays per game than Oregon, but they're 8th overall. They go to the Rose Bowl, meaning they did really well. They lost it, but they got their final rank as 11th. That's really good for a first-year head coach and before an Oregon Duck program in a really tough conference. 2010, they go 12-1. That's a great record. They run 78 plays a game, almost 79. It's incredible. That's a huge difference, massive difference. And guess what their offensive ranking was? 1. Scored 611 points. That's what is that, like 49 points a game? That's like video football, fantasy. It's crazy. Yeah, but you know why? Right here, well, they went to the college BCS championship. They lost it to Auburn because Auburn had a great defense, and a great defense can stop an up-tempo, no huddle offense. But getting to the dance, you get to dance with the pretty girl. That's the goal. And I suggest to you that even though there's no causation, there's a strong signal there. I think there's a strong correlation. And in 2011, they run 72. They win the Rose Bowl, final rank 4. Last year, they're running, my God, 81 plays a game. That's just unheard of. They're number 2 in offense in the nation. They win the Fiesta, final rank 2. That's just incredible. So I suggest that there is some evidence that there's something to this up-tempo, no-huddle offense. So forecasting, you know, I could spend an entire 2-hour presentation just on this chart, talking about it. What I think I want you to get out of it today is that there's a framework, there's a process for doing forecasting. So again, you know, which is also predictive. They're interchangeable. So I kind of predict that more teams in the NFL are going to use the no huddle or a variable huddle, no huddle offense. In fact, Chip Kelly, who's the head coach at Oregon, is a rookie head coach, first-year head coach at the Philadelphia Eagles. So he's bringing it to the NFL. But Bill Belichick has already been doing it. Peyton Manning's been doing it. Indy did it last year with Luck. I think the statistics say that Seattle is running some form of a variable tempo. So they're experimenting with it. And so my prediction is that more teams will play faster to get more plays per game. What you need to take out of it today is that you formulate a problem, you get information, you get methods, you implement them, you evaluate those methods, you make a forecast, and then you keep track of your forecast. You're going to be wrong a lot. You know, I have a friend who's a professional gambler, and he tells me that he has to be right 57% or more in order to make money, to make enough money, to make it worthwhile. And I said, well, what if you're 60% right, meaning you're going to be 40% wrong? He said, I'll make a decent living. That means he's still 40% wrong. This guy uses, you know, Bayesian probability. He's got a brain like a computer. He lives well, makes a lot of money. So some forecasting methods. You want to make sure that you have good quality data. Quantitative methods or statistical methods, and then judgmental methods have to do with experts and opinions. Evidence strongly suggests that doing both quantitative and judgmental methods and merging them together will give you more accurate forecasting than just using one or the other. That's the important thing to take away today. This is the different methodologies of judgmental or statistical
forecasting. I could spend a 2-hour presentation on each one, and in the future we will. But what you need to know today is that there are a number of different methods that you can use. And if you gain experience and you become an expert in using these methods, companies will pay you a lot of money to help them make forecasts. So I want to show you a few interesting charts. Change in offensive play calling. This chart just basically shows that there are more passes that are being thrown in the NFL than runs. I think that the ratio is 60-40 pass to run, but you have to ask yourself why. Well, average pass attempts per game in the last 35 years. Interesting, in 94, 95, there was a peak and then it came down. It'd be interesting hypothesis to find out why. Perhaps defenses figured out what the offenses were doing and caught up and were able to stop them. Then the offenses tried something new, defenses figured it out. But anyway, it's been a steady progression up to more pass attempts per game. Well, I asked myself why. Can the data tell us why? Completion percentage has been steadily going up. I predict that the reason is quarterbacks are getting better at their craft. They're throwing more accurately, but also they're throwing more timing, shorter passes to reduce the risk of interception. So interception rate in the last 35 years has gone down tremendously. And again, I think that's because offenses are using timing patterns to reduce the risk of interception, as well as the quarterbacks coming out are just more accurate. So what it basically says is that your risk-reward probability is better for passing than it is for running. Now you still need to run. Run is important because you need to give your defense some rest. You just can't go bang, bang, bang and score and have your defense go back on the field or you're going to wear your defense out. And also later in the season, when you get to the playoffs in December and January, the weather gets bad. And when the weather gets bad, you can't pass as efficiently. So it helps to have a good running game. Also, in the fourth quarter, if you get a lead by passing, you can protect that better by playing slow ball. You want to speed the clock up to run the clock out on the opposition, and you can do that by running, which takes more time off the clock. The important thing is that you get a greater reward for passing than you do for running. And that is causing teams to want to pass more. Quarterback ratings, again, going way up, a steady line going up. And again, I think this is because of shorter pass attempts. Also, I think the up-tempo, no-huddle offense is catching defenses off guard, and quarterbacks are just getting better trained and more accurate. Series first down likelihood on 1st and 10, again, you have a much greater likelihood of getting a first down if you pass the ball than if you run the ball. So, offensive points by yards. Now, we all know teams that sometimes gain a lot of yards but don't get a lot of points out of it. But the truth is, on average, the more yards you get, it's correlated with the more points you're going to score. The more points you're going to score, the more likely wins that you're going to have. So season wins by passing efficiency. Again, it's becoming a passing league. What is all this data basically telling us? It's saying, well, you've got to play fast. You've got to do a no-huddle, up-tempo. You've got to throw the ball, pass the ball very well, pass more than run. But prescriptively, you're a data scientist. What do you tell your client? Well, what you tell your client is you need to get a really, really good quarterback, right? Right? So that's where we have to put on our thinking caps. This is all the charts that I've been showing you.
has been telling you, we got to have a good passing game. We need to get a really good quarterback. We need to have a strategy of up-tempo and variable tempo, no huddle. Now, prescriptively, how do you get there? You know, plays per game. This goes the other way. This kind of confused me at first. 1940 is basically showing that we're passing a lot more than you're running. But interesting, in 1979 is where the convergence. And there's a reason for that. You want to know what happened in 1979? They changed the rules. So the defensive backs can't touch the wide receivers anymore. Hell, you can't even breathe on them. You breathe on a wide receiver, you're going to get flagged for pass interference. Well, data shows what happened. You change that rule so that you can hit the wide receiver after 5 yards, guarantee you the whole game changes. The whole game changes. So prediction. More NFL offenses are going to utilize the variable tempo, up-tempo, no-huddle strategy. More NFL offenses will pass. And NFL teams using the up-tempo, no-huddle strategy will have the best winning records. Now, again, I didn't prove that. But I think in the future, that's what's going to happen. I also predicted a lot of teams are going to try this, but they're not going to recruit the right talent to be able to run it, especially quarterback. You have to have a really special quarterback who is really intelligent, because if you're not huddling up, you're calling your own plays, and you're getting to the line of scrimmage, and you've got to read the defense in front of you. So I think it's more mental than anything. And, you know, you got 12 big, fast dudes who have one objective in mind, and that is to hit you hard and hurt you. You know, it may sound easy, but I think actually playing NFL quarterback may be one of the toughest job positions, along with Navy SEAL, in the world. I also predict that some really good defenses will stop any good offense. And even a Tom Brady-led no huddle, up-tempo, a really good defenses we've seen, like the New York Giants or other teams, can stop this sort of offense cold in its tracks. But I think you have to look at the averages. And if I'm an NFL owner, I'm going to want to get a coach who understands the passing game, who knows how to recruit a good quarterback and talent around him, and is going to institute this type of strategy. Thank you.
So before I get into visualizing data, I do want to take a few minutes to very quickly cover Shark in more detail than was covered earlier. Shark is SQL-ish on Hadoop. It uses HiveQL, so I never call HiveQL SQL because it's not. It's close, but they're not the same. I don't have any slides on it today to show you, but in particular from a performance perspective, when you have your entire data set cached in Hive, and I've seen this with a 1 GB data set, cached in Shark, not Hive. Let me get that correct. When you have your entire data set cached in Shark in memory, I've seen that Shark is 70 to 100 times faster than running it in Hive on a 1 GB data set. Yeah, that's not a very big data set, but that's what I had to play with. Now, when you don't have your data cached, you have none of your data cached, I've only seen performance improvements over Hive of 1.5 to maybe 2 times faster. So if you're really going to get the performance improvements out of Shark, you really want your data cached in memory, which of course has the issue of memory and mapping. Shark stores everything in memory, and MapReduce likes lots of memory too. So how do you make them run on the same cluster happily? But that's a big administrative question that I'm sure you don't really want to get into. The other thing to talk about with Shark is it is not an enterprise replacement to the database. Yes, there is a JDBC server, but the JDBC server is built on an older version of the Hive server that is not designed for concurrent connections. So the Shark JDBC server is designed for one person to be connecting to it at a time. When you start having multiple people connecting, and especially if one of those queries fails, it has a habit of taking down the Shark server. It's an issue with Hive today too. They've actually recently released a new version of the Hive server designed for concurrent connections. I am sure as the Berkeley team continues to work on Shark and Spark, they will upgrade to the new version of the Hive server and be designed for concurrent connections. It's just, don't plan on deploying Shark to a 100-person group today without having 100 Shark server instances. But yeah, when you're using Shark command line, very fast, you can have lots of people using the Shark command line, just not through JDBC, which also has the impact then that your JDBC clients, your reporting tools, connecting those to Shark also has the same JDBC issue. That's probably all I have really to say on Shark, but did want to cover it in a couple minutes. As far as visualizing data, one question I always like to ask data scientists is, when does the data scientist's job end? You know, some data scientists will respond, well, it ends after I create the model. I don't think that's true. The data scientist has to create the model, but they also have to be able to build the story around the model and be able to show to you what the model is doing for your business, what the model, show the business users what the model is doing for them. Otherwise, it's some black box and they look at it and they go, okay, so what's that model doing? And they go, I don't know, they just tell me to use it. So I think from a data scientist, not only do you have to model, and that's probably 10% of your job because the first 80% is cleaning up your data. But I also think I think there's 5% of building visualizations around it and probably 5% of telling the story. So when does a data science job end? So, you know, talking to your audience about regression analysis and data ranks, not all your business users are going to understand those terms. Instead, it's going to deliver, you're going to sell 50% more product if you follow this, if you use this. And you must be able to present your findings in a way that's non-technical and easy for the business users to understand. So which would your manager prefer? Or probably a better question is, which would your CEO prefer? Do they want an Excel sheet of a bunch of numbers to look at? Or would they rather some sort of visualization where they can actually look at a graph and quickly see what you're trying to get across and not have to look through a bunch of numbers and figure out what those numbers mean? I personally prefer this. I'm sure there are some CEOs out there who prefer the graph, but who prefer the Excel sheet. But I generally I think business users want the graph. So there are a whole bunch of big data visualization tools. These are just a small number: Pentaho, Tableau, Jaspersoft, Pervasive, Burst. I could go on and on and on. You know, I could go D3 and others. I'm specifically today going to talk about Pentaho, mainly because Pentaho is what I know. Pentaho has a free desktop visualization tool. So it's free and not like Tableau or some other tools that are rather expensive. So that's what I'm using. So Pentaho, just a quick overview of Pentaho. They're an open source suite. They have a full data integration business analytics platform. So they have data integration tools. They have pixel perfect reporting, your old PDF reports. They have OLAP cubes for slicing and dicing the data, and they have your business dashboards that contain multiple pieces that refresh every 10 minutes. They worked with most of the big data sources out there. So you can connect Pentaho with Hadoop, Hive, HBase, Cassandra, MongoDB, Couchbase, and along with the traditional databases and your Excel files. They have a Salesforce. They have Salesforce integration, Google Analytics integration. You name it, you can probably integrate with it. And their OLAP engine uses Mondrian, which is a OLAP cube builder, to automatically generate the SQL against your database. So you're not sitting there writing SQL all day. Pentaho has integration with Weka. We can all grow, I understand. But that's their only statistical language integration today. What I have seen a lot of companies have been doing who use Pentaho is they may go build their model in R, export that to PMML, and then import that into Weka and use Weka as their actual engine to run the model. That way they can integrate it with the rest of their data integration capabilities and the rest of their data integration flow. Unfortunately, like most of the other data visualization tools out there, Pentaho for the slicing and dicing visualization still has to have a fully compliant SQL. There's been some work around making it work with HiveQL. It's not there yet, obviously until the past 6 months or so when the speed of thought Hive engines have started to appear, such as Shark and Impala. There hasn't been a whole lot of need for slicing and dicing HiveQL integration because, well, you go and run a Hive query and it takes 3 days to return. We're not exactly slicing and dicing there. And yes, I have had Hive queries take more than 3 days to return. So it's something that I'm sure they're working on. I don't know where it is in the process, when you may see it, but it's something I'm sure everybody out there is going to be working on. Is A, making HiveQL more ANSI SQL compliant, and B, the vendors creating dialects to work with HiveQL. They do have a commercial edition that automates some of the things I will show you today, makes it a slightly bit easier, that also takes the slicing and dicing and makes it available on the web. Today, although I am using the commercial edition version on my laptop, I'm only showing free edition capabilities. So that's the end of my slides, and now I'm actually going to show you something. Okay. Let me. Okay. So what I had to do was I took our input data, I processed it with Shark, and then I had to, because it's not compliant, it doesn't work with the HiveQL, I had to extract that data from Shark to an actual database. So you're going to extract a subset of your data, most likely, some aggregation of your data to a database. Could be an in-memory database, such as MonadDB. I'm sorry to see a lot of that. It's actually what Pentaho's InstaView product, which is commercial edition, does, is it will automatically export it from Shark or Hive or whatever into a MonadDB database. And then I'm simply outputting it using a table output directly into my SQL database in this case. Again, MonadDB, Vectorwise, any database out there you can think of. If it has a JDBC driver, Pentaho can use it. I can then go and visualize this table. It's going to pull up, it should pull up what Pentaho calls analyzer. Try this again. Good thing I pulled it up earlier. And what you can do is you can drag your fields onto the onto the screen, and it's going to automatically run the SQL. I'm not writing the SQL to do this. It's going to automatically run the SQL against the database to create those aggregations. So I actually didn't want to pull count plays. So if I wanted the number of plays by team, all I have to do is drag them on the screen, and I have that information. I can then some of the visualizations Michael was showing earlier, I could say I only want the top, let's say 5 teams by the number of plays. And then I can go and say, hey, I want to create a graph on this. And it's going to, let me go and resize a few things. It's going to go and automatically create a graph. I can then, let's say though, I want this count of plays, but I want to look at it by the type of play it was. So I can actually automatically create a stacked graph. Obviously with the font size, let me change the font size real quick. Font size looks so much better when you're using it on your laptop. No, not a 20-foot screen. So I can actually go and look at this, and I can say that these are the number of completed passes, these are the number of, I think, incomplete passes, this is the number of runs that each team did over this 9-year span. But I want to actually look at that by season. So I can drag on season and wait a minute as it refreshes. And go and decrease this font size even more. And I get a chart for each season, the number of plays within that season. And I have a whole variety of chart types. So I can do a heat grid, although I suspect I'm going to have to modify what I'm actually trying to show here. How does this work? So a heat grid of by season and by team, the number of types of each play. So let's go look at something else. Let's go look at, let me go to remove everything from this report. Let's say, as Michael was bringing up earlier, we talked about last night as we played with this, the number of plays by minute, the number of scoring plays by minute. Well, first off, as you can clearly see, there are some data quality issues. There obviously is no negative 15 in the game. And I want the number of scoring plays. Go ahead and exclude where it's not a scoring play.